Hi, welcome to the Euclidean Geometry 101 course. This is part 3 of the series. We're still in the chapter about angles, and in this part we'll continue defining properties of angles. In the previous lesson, we've defined a few types of angles. We will talk about 2 other types of angles, but to do that we'll have to define a few operations that can be done with angles, similar to what we have defined for line segments. First of all, we define the equality of angles. 2 angles are equal when we can make the vertex and the legs coincide with each other. In the figure B', A' can be placed on BA, and B'C' can be placed on BC. But as we do not consider the direction of the angle, we can also place B'C' on BA and B'A' on BC. We can add angles together. This is done by making them adjacent angles. Take for instance 2 angles, ABC and CB'D. By moving CB'D and having B' coincide with B, and make one of the legs a line, we get an angle ABD, which is the sum of the 2. Lastly, we say that an angle ABD is bigger than ABC if the first one is equal to the sum of this angle and another angle. That other angle, in this example, CBD, is the difference. We can, of course, also multiply angles by an integer, and we can also divide angles. A special case of angle division is the one that divides the angle in 2 equal angles. The line that divides that angle is called the bisector of the angle. By the same reasoning we followed while proving proposition 1, we can prove that a bisector can always be constructed and that there's only one for each angle. Now that we've defined the sum of angles, we can introduce 2 types of angles. What we're seeing here are 2 supplementary angles. We call 2 angles supplements of each other when the sum of the 2 angles is equal to 2 right angles. We can also define complementary angles. As you can see in the drawing, this occurs when the sum of 2 angles is equal to a right angle. We're now ready for proposition 2. If the outer legs of 2 adjacent angles are in line with each other, then the angles formed are each other's supplements. Let's prove this. Take AOC and AOB. Their outer legs OC and OB are in line with each other. Now construct the perpendicular in O on BC. We have AOC equals COD plus DOA, and AOB equals DOB minus DOA. Let's take the sum of both sides of the equation. We get that AOC plus AOB equals COD plus DOB. But COD and DOB are right angles, so the sum is 2 right angles, and that's what needed to be proven. The converse of the proposition is also valid. If 2 angles are each other's supplements, then the outer legs are in line with each other. Let's prove this. So we know that the sum of angle AOC and angle AOB is equal to 2 right angles. We need to prove that OB and OC are in line with each other. Let's use the technique of proof by contradiction. We assume that OB is not in line with OC. And let's call OB prime the ray that's in line with OC. Two equalities are now clearly valid. The first one, the sum of angle AOC and angle AOB is equal to two right angles, because this is given. The second one, by applying the direct proposition we have that the sum of AOC and AOB prime is equal to two right angles. Let's now subtract the two sides of the equation. We conclude that angle AOB must be equal to angle AOB prime. So that means that OB coincides with OB prime, or OB is in line with OC. There are some corollaries to this proposition. First of all, if one of the angles that are in line with each other is a right angle, the other will also be a right angle, so a right angle is equal to its supplement. Secondly, the sum of all adjacent angles on one side of a line is equal to a straight angle. Thirdly, the sum of all consecutive angles around the same point is equal to four right angles, or a full angle. Let's show this on an example. We start with angles AOB, BOC, COD, and DOA. We need to prove that their sum is four right angles. Let's extend AO with OA prime. We now have an equation where the sum of the four angles is equal to the sum of all the angles on one side of AA prime and the sum of all the angles on the other side of AA prime. And since the sum of all adjacent angles on one side of a line is equal to a straight angle, we can say that all the angles on one side of AA prime have a sum of two right angles, and all the angles on the other side of AA prime have also a sum of two right angles. This leads to the conclusion that the total sum is four right angles. We have proven this for these four angles, but we can do this for any number of angles around a vertex. When three or more straight lines pass through the same vertex, they are called concurrent lines. And a last corollary states that the supplement of an acute angle is obtuse, and conversely, the supplement of an obtuse angle is acute. We'll finish the lesson of today with an observation regarding perpendicularity. Perpendicularity is symmetric, which means that if a first straight line is perpendicular to a second straight line, then the second straight line is also perpendicular to the first. That's it for the third lesson. Next time, we'll wrap up this chapter about angles. If you like this series, consider subscribing to my channel.